We are now going to take a very short little break from computing integrals and define the concepts of divergence and curl. So right now on the screen, I have written down some definitions of divergence and curl. Divergence will measure the tendency of a fluid to collect or disperse at a point, and it's going to be a scalar, so just a number. So for example, you could think of it as when you're stuck in traffic, the cars are converging, they're coming together. That's why things are slowing down. When traffic eases up, the cars are starting to diverge, and that's what that divergence is measuring. Really useful when we're talking about airflow or water as well. Curl, on the other hand, measures the tendency of a fluid to swirl around a point. So if you're thinking about maybe eddies in the air or in water, you might want to measure the curl. And when you compute the curl, your answer is actually going to be a vector. All right, so here is how we compute the divergence of vector f. We take the derivative of the x component with respect to x plus the derivative of the y component with respect to y. And one way that this is denoted is sometimes people denote this as del dot f. So you can think of this del symbol perhaps as this vector that is d dx d dy, and you're dotting that with your vector field. So this mx plus ny quantity might look familiar. This is what we were integrating in the flux form of Green's theorem. So when we wanted to compute the flux across a path, Green's theorem actually told us we could integrate the divergence over that area. So that was our flux form of Green's theorem. We were actually integrating the divergence. We can have divergence for, or talk about divergence for vectors in 3 dimensions as well. We just have that extra component. We'll take our z component, derivative with respect to z, tack that on there. All right, so that is divergence. And so if you want to compute the divergence, and divergence is also just abbreviated as div. So if you want to compute the divergence of vector field f, what you're going to do is you are going to take the derivative of your x component, which we're calling m, with respect to x, y component with respect to y, z component with respect to z. So in this case, the m is the x squared, or no, it's xy squared z. So its derivative with respect to x is just y squared z. The n is z to the third, doesn't have any y's in it, so n sub y is 0. And derivative of the p, derivative of x cosine yz with respect to z, I'm going to have to use a chain rule on this one. X stays there. I get a negative sine of yz, and then there's the chain rule part. I have to multiply by the derivative of the inside. Derivative of yz is y. And then finally, we are going to add these things together to get our answer. So divergence of vector field f is y squared z plus 0 minus xy sine of yz. Notice that my answer is no longer a vector. It's going to be a scalar, or in this case, just a function that is not a vector. A harmonic function is one that the divergence of the gradient vector equals 0. And so we actually sometimes denote this divergence of gradient vector as del squared f. That's something you might see in other classes. So our question is the function x squared minus xyz harmonic? So first thing I'm going to do is compute my gradient vector. And then I'm going to find the divergence of that gradient vector. So gradient vector, I take the derivative of the function with respect to x. I get 2x minus yz. Derivative with respect to y is just negative xc. And derivative with respect to z is negative yz. So there's my gradient vector, which consists of those partial derivatives. And now I'm going to find the divergence of that gradient vector. So I'm going to take the derivative of my x component with respect to x. I get 2. Y component with respect to y, I get 0. Z component with respect to z, I get 0. And what we're actually doing here when we find this del squared f, technically what we're doing is we took our derivative with respect to x and then found its derivative with respect to x again. And then we took the derivative of the function with respect to y, found its derivative with respect to y again, took the derivative of the function with respect to z, and found its derivative with respect to z again. So we're technically finding second partial derivatives, I guess. Regardless, what is the question? Is this a harmonic function? The divergence of our gradient vector is actually 2. 2 plus 0 is 2. And we were told in the instructions that a harmonic function is one that has a divergence of its gradient that is 0. So that's not 0. The answer is no, this is not a harmonic function. All right, so the second quantity I wanted to define is the quantity curl. And curl is a vector quantity. So if you have a two-dimensional vector, mn, your curl is defined to be nx minus my, and it'll point in the k direction. One thing I'd like to point out, this nx minus my is actually the quantity that we were integrating when we were using Green's theorem in that circulation form. We were actually integrating our curl for the circulation form of Green's theorem. Okay, so curl is nx minus my. For two-dimensional vectors, that curl is actually going to point in the z direction. If you have a three-dimensional vector, I have this big, long formula for curl. But one way you can think about this formula, I'm not even going to read it all out loud, there's so many letters on there, is I think of this as del cross f. So you can treat this like a cross product. And you can set up your cross products like we've done in the past in this determinant form. So you can put in the I, the j, the k. The del, you can think of as a ddx, ddy, ddz. And then just list vector f, m, n, p. And then you can actually arrive at this big, long formula I have on the screen by just applying our rule for finding cross products. So for the I component, I cover up the column with the I, and then I'm going to take dp dy minus dn dz. And then for the j component, it's going to be negative, so don't forget to put that negative in there. Cover up the j column, and then we take dp dx minus dm dz. And then finally, the k is a plus. And then we'll take dn dx minus dm dy. And what I have written down is the exact same formula I had typed onto my screen. So that vector is going to be the curl of this vector field. So let's do an example. Let's see if we can find the curl of the vector field xyz, comma, x squared y squared, comma, xyz to the third. So I just wrote out my determinant, just to help me kind of remember what is that formula for curl. So let's see, the m is x, y, z. So I'm going to go ahead and find my derivatives. Derivative of m with respect to y is xz. M with respect to z is xy. N was x squared, y squared. Derivative with respect to x is 2xy squared. With respect to z is 0. My p was xyz to the third. Derivative with respect to x is yz to the third. With respect to y is xz to the third. So I have all my derivatives written down. And now I just plug things into the formula. So I'm going to take dp dy minus dn dz, and that's going to be my I component. And then for the j component, we're going to do a negative, and it's going to be dp dx minus dm dz, and don't forget to make it negative. And then finally for the z, or the z component, we'll take dn dx minus dm dy. And this vector is my solution. When you're computing curl, your answer is going to be a vector. So that kind of complicated vector is the curl of this function. So one thing I want to kind of point out while I have this problem on the screen, I don't know if any of these kind of idea of the finding all these partial derivatives look familiar to you, but what this reminds me of is when we talked about conservative vector fields. When we talked about conservative vector fields, we actually kind of went through this process to see if something was conservative, and we actually figured out that, or we talked about the fact that if the nx and the my are the same, no, they're not here, so this is not conservative. But then we also had to compare the mz with the px. And then finally we had to compare, it was the nz with the py, to see if those things were the same. Technically what we were doing when we did this process is we were actually determining whether or not the curl was 0. And so I bring that up now because I have all these derivatives written on my screen. I will write that down in a couple other slides, but just to kind of connect this, I guess, to some things we've talked about in the past, our conservative vector fields are vector fields that have a curl equal to 0. All right, let's do one more example. Let's see if we can find the curl of the following vector field. So I'm going to jot down my formula. My m is sine of z, the n is the negative z sine of y, p is the x cosine z plus cosine y. So I found the derivative of m with respect to y and with respect to z. I got 0 and cosine z. Then I found my derivative of n with respect to x, it's 0. With respect to z, negative sine y. And then I found my derivative of p with respect to x, just cosine z. Found my derivative of p with respect to y, negative sine y. So while I have these derivatives up on the screen, notice for this one, the my and the nx are the same. They're both 0. The mz and the px are both the same, cosine z. The nz and the py are both the same. So we have just shown actually that this is a conservative vector field. This is a vector field that has a potential function. And in fact, if I go through and I compute the curl, so I use my formula, I take py minus nz, And then I take px minus mz. And then finally, nx minus my. My curl is 0. I get the 0 vector for my curl. And in fact, that is going to happen anytime you have a conservative vector field. And so that is what I have written on the next slide. A vector field will be conservative if and only if its curl is equal to 0. And so you could also say if the curl is equal to 0, then it is a conservative vector field. All right, so I am going to stop there. The point of this section was really just introducing you to these definitions, divergence and curl, which did pop up in Green's theorem. And then just looking ahead, where we're going with this is we are going to kind of extend Green's theorem to 3 dimensions. That's really our goal. And think about how divergence and curl are going to play a role in those extensions. All right, as always, let me know if you have any questions on this video.